Hi, my name is Jason Hinkle, and I'm a third-year graduate student at the Institute for Astronomy. I work with Ben Shappy in the All-Sky Automated Survey for Supernovae, or ASSASSIN team, to study tidal disruption events. A tidal disruption event, or TDE, occurs when a star passes too close to a supermassive black hole in the center of a galaxy and gets ripped apart. As a fraction of that disrupted stellar material falls back onto the black hole, it causes a luminous flare. In recent years, with the growth of ground-based transient surveys, particularly those associated with the University of Hawaii, this has fueled a rapid increase in both the number of discovered TDEs as well as a growing diversity of TDE properties. The reason I'm interested in studying TDEs is because they're promising probes of supermassive black holes, particularly those at large distances. Currently, the only way we can study supermassive black holes is if they live in a nearby galaxy. This is because we need to resolve the orbits of stars or gas in the supermassive black hole's sphere of influence, which is incredibly small when projected on the night sky. Alternatively, we can study actively accreting supermassive black holes, also known as active galactic nuclei, to infer properties of the supermassive black hole, such as their mass or spin. However, only about 10% of all galaxies host an AGN, and therefore such a sample is not representative. Unfortunately, though, the use of TDEs as probes of black holes is stalled by our lack of knowledge on TDE physics itself. The most notable gap in this knowledge is what powers the UV optical emission from TDEs. Two main theories on this exist, one where the emission is powered by shocks within the tidal debris stream, and the other where an accretion disk is rapidly formed and high-energy X-ray photons emitted from this disk are reprocessed by an optically thick outflow and re-emitted at longer wavelengths. However, due to similar energy budgets and a lack of observational predictions, we simply do not know which emission mechanism is at play. My thesis in particular focuses on creating a homogeneous sample of TDEs with multi-wavelength data that we can use to search for trends that may give hints on the underlying TDE physics. My work uses both multi-wavelength photometry and spectroscopy to understand the broader TDE diversity, as well as interesting aspects of the temporal evolution for individual objects. By establishing a sample of well-observed TDEs, we can constrain the presence of strong trends within these properties and can test existing theoretical models, as well as inform future studies to understand what actually powers the observed emission from TDEs. With this knowledge, we can finally begin to use TDEs as probes of supermassive black holes.